Good morning everyone, it's day 21 and this is Anagon Live. I'm ready to go and I'm very happy to keep going with Advent of Code because yesterday I was able to solve a puzzle that got me stuck very much, and that was actually day 20. That was yesterday's puzzle. I am having a bit of a hard time to keep up with all of the different puzzles that are there and which ones I still have to do. You can see on the right here that I'm still working on puzzle 18 and 16, but yesterday we had a puzzle with a maze and I spent really a long time on it. It's not that I didn't know how to solve it. I think I did have the right approach. I was using breadth first search, as most people would probably do in this case, but it just kept running and running and running. And I didn't understand really why. I thought I had all the elements of breadth first search. I had a list of nodes to visit, I had a way to expand them, I had a way to check whether or not to visit them, and I didn't have a way to predict the cost, because in breadth first search you don't need that. You just need to always continue with the shortest path that you have so far. But what it turns out to be, it's after I looked at Alex's code to see how he solved it, I realized that I'm actually not checking whether or not I've visited that location yet or not. I did have a check for that, but I didn't check it in the right position. So in breadth first search, excuse me, when you are going to decide which nodes you're going to visit, at that point you need to see, have I visited it before? And the trick here is, when are you going to label a node as being visited? Is it when you are actually going to pop that node from your queue and evaluate it, or is it when you add it to your to visit list? And it turns out you have to add it to your visited list when you're adding it to your to visit list. So what it looks like in my code on the left is like this. Let me see where my code starts. So here I have a loop that goes over the list of moves that we have, and here I'm deciding which, oh, this is actually day 18, so that is not the one I wanted to show you. So it's day 20, and here is part 2, and I have my loop here, and I'm popping my tiles. I'm popping from the tiles I want to check, and here is the part where I'm checking all of the directions. And now, so here's the essential part. So I'm checking if the direction around me that I might check is a walkable tile. So that is a kind of basic check that you would not forget, of course. But then the second check is, have I not already added it? Or have I actually not already checked it? And so here, when you decide I haven't checked it yet, then you're going right away to mark that tile as being checked, which kind of intuitively doesn't make a lot of sense, because for me it feels like I haven't really checked it yet. I've just added it to my list. So you could solve that, of course, by using a different variable name. But once I added my node to the checked tiles list right away, after adding it to my to-do list, so to say, suddenly it started to run very fast. And I think I did have some other bugs to fix first, but rather than expanding more than 1 million times and still not finding an answer, it was running for just a few 100,000 times, and then it found the right answer. So I think this is also the problem I'm having with day 18, and I am going to try also today to fix day 18. I'm almost there. And so that is my biggest lesson for Advent of Code 2019, how breadth first search works. And I still have to kind of learn if there are any differences with A star, if your node checking is different in A star or not. I'm not sure, but I feel like probably yes. So we are getting ready for day 21 already. We have a few seconds left. So I wish everyone good luck on day 21, and please do come by if you're done and you want to share some code or just have some fun. Good luck! Day 21. Springdroid Adventure. You lift off from Pluto and start flying in the direction of Santa. While experimenting further with the tractor beam, you accidentally pull an asteroid directly into your ship. It deals significant damage to your hull and causes your ship to begin tumbling violently. You can send a droid out to investigate, but the tumbling is causing enough artificial gravity that one wrong step could send the droid through a hole in the hull and flying out into space. The clear choice for this mission is a droid that can jump over the holes in the hull, a Springdroid. You can use an int code program, your puzzle input, running on an ASCII-capable computer to program the Springdroid. However, the Springdroids don't run in code. Instead, they run a simplified assembly language called SpringScript. Yes! I'm so happy and excited to hear that. I was looking very much forward to actually implement a higher level language on top of int code, although I'm very scared of what we're going to have to do. It might not be easy at all, but the first time I'm ever going to write an assembly language. Let's see how that goes. So while a Springdroid is certainly capable of navigating the artificial gravity and giant holes, it has one downside. It can only remember at most 15 SpringScript instructions. The Springdroid will move forward automatically. Oh, maybe. Wait, do we have to compile an assembly language into int code, or do we actually pass this int code script into the computer and it's going to run that? But if that's the case, then it means that the assembly interpreter is running inside the int code program that is our input. That would be less cool, but still kind of cool. So it can only remember 15 SpringScript instructions. The Springdroid will move forward automatically, constantly thinking whether to jump. The SpringScript program defines the logic for this decision. The SpringScript programs only use Boolean values, not numbers or strings. Okay. 2 registers are available: T, the temporary value register, and J, the jump register. If the jump register is true at the end of the SpringScript program, the droid will try to jump. Both of these registers start with the value false. Okay. Springdroids have a sensor that can detect whether there is ground at various distances in the direction it is facing. Hey Eric, good morning. So it seems like we're going to do something with assembly, but I'm still not sure if we're going to just write a Springdroid script or if we're going to write an assembly interpreter. Springdroids have a sensor that can detect whether there is ground at various distances. These values are provided in read-only registers. Your Springdroid can detect ground at 4 distances: 1 tile, 2, 3, and 4 tiles away. If there is ground at a given distance, the register will be true. If there is a hole, the register will be false. So that means that, let's say we jump 1 tile at a time, like skipping 1, we cannot jump as soon as we detect a hole. We have to memorize that 3 steps ago we found a hole, something like that. There are only 3 instructions available in the SpringScript, and XY sets Y to true if both X and Y are true. Otherwise it sets Y to false, or XY sets Y to true if at least one of X and Y is true. Otherwise it sets it to false. Not XY sets Y to true if X is false, otherwise it sets Y to false. So we have input instructions like input parameters X and Y, and the output is actually the second input parameter. So I guess these are kind of relative distances or something. In all 3 instructions, the second argument needs to be a writable register. The first argument, X, can be any register, including A, B, C, or D. So do we pass it as ASCII then? I guess. So I guess we pass it as ASCII characters, so that means we have to write our program in normal text and then send the ASCII key codes to the int code computer. For example, the 1 instruction program, not AJ, means if the tile immediately in front of me is not ground, jump. But but I thought it would look, okay, it looks 4 ahead, but you do have access to the reading values of each tile ahead of you. So you don't have to memorize 3 steps. So Y needs to be a writable register, and the first can be any register including A, B, C or D. For example, the one instruction program not AJ means if the tile immediately in front of me is not ground, then jump. Okay. Or there is a program that jumps if the 3 tile wide hole, if a 3 tile wide hole is detected with ground on the other side of the hole. Then how does it work? So we don't have ground, then we need to jump. If we don't have, how does that work? And what does T actually do? So J is jump and T is a temporary value register. Okay. So if we don't have an empty space, no, if we don't have ground, then we jump, and also if there's no ground after that, then we keep this value in T, and if T is correct, or T is true, and J is already true, then what? Then we're storing true in the jump value. So basically that is kind of a logical conjunction where you can say both there must be no ground in front of me and there must be no ground in front of me 2 steps ahead, and if those are both true, then we're going to jump. And we're double checking again with C. So C is stored in T, or not C is stored in T, so that means there's no ground. And then if there's no ground and we were gonna jump, then we're gonna still jump, otherwise not. And here for D, if there is ground in D, then we're going, and we were going to jump, then we're going to jump. So because you can't make like very complicated logical expressions, you're going to have to do it like step by step and using the temporary register to store values. And especially you cannot invert values other than taking a negative like not and storing it in a temporary register. So that I think helps me understand how it works on a basic level. Then the intcode program expects ASCII inputs and outputs. It will begin by displaying a prompt, then input the desired instructions, 1 per line, and each line with a new line. And when you have finished entering your program, provide the command walk, followed by a new line, to instruct the Springdroid to begin surveying the hall. If the Springdroid falls into space, an ASCII rendering of the last moments of its life will be produced. In these, an @ sign is the Springdroid and a hash is the hall, and dot is empty space. For example, suppose you program the Springdroid like this, not DJ, that means there is no ground store, whether there is no ground in the jump register. So if there's no ground 4 steps ahead, then we are going to jump, and then let's say we walk. So this one instruction program sets J to true if and only if there is no ground 4 tiles away. In other words, it attempts to jump into any hole it finds. So how does it really jump? So right here, this is the place where it's going to jump, and it goes 1 up, 1 more up, then 1 to the right, and then 1 down. So that is a jump. It is actually going to skip 3 steps exactly. And it takes some time also to make the jump. However, if the Springdroid successfully makes it across, it will use an output instruction to indicate the amount of damage to the hull as a single giant integer outside the normal ASCII range. So that is like bigger than 127. Program the Springdroid with logic that allows it to survey the hull without falling into space. What amount of hull damage does it report? Alright. There are quite a bit of instructions in here. And let's see, we don't have to actually implement those jump registers. We just need to think logically what we should program the robot with. So I'm going to go to day 21 and create a Python file. I haven't done that yet. So that's day 21. And I'm going to download my input for today. That is right here. So after reading the puzzle so far, do you have an idea how to solve it yet? I think I don't, although it seems that generally you need to land exactly after. Yeah, for Eric I understand that you have some ideas, of course. But my current idea is that we always want to land right after a hole. But of course you do have cases where you have two holes like right after each other, and then you need to think strategically where you're going to land. So maybe we need to think about that before we actually implement our program. I'm not sure. Well, let's start by being able to input and output data to and from the encoder computer, and then come up with a strategy. So we have our robot, and it's called a Droid, Springdroid, and that will be an int-code computer from day 9. Let's see, I think I called it int-code computer day 9. Yes. And now another thing I did notice, I think that we need to keep running with the same computer, so we just gotta run it until we need input. That means I can just load the file once, load from file, day 21 input.txt, and let's run it also. Run program with no inputs. Maybe we do need to give it an input like walk. What I see a lot of people do is actually create a little class like Springdroid, for example, and then put the computer inside it. I think it's nice, and I want to try doing that today. So we need an init that would load the input file, and then here I'll call it computer. And I'm going to store that, of course. Self.computer. And maybe we can just say that we want to start it like this. And that would run until we need input, I guess. And the output is going to be provided here. And after we have some output, we can print it. So we can go over all of the output in there. And those are going to be ASCII characters, so we can print them using CHR without line ending, because line endings are output explicitly by the robot itself. So that is the start. So let's see if we can run this and what output we get. Like this. Run day 21. And we do get a lot of output, but it's actually from my computer. It's showing what it's doing internally. So I'm going to tell the computer not to output any debug information. Debug is false. And that didn't work because I need to reference the computer and not the Springdroid. So now we see input instructions. We have a chance to input some program. And that means that we have to define the program. Okay, so how can we do that? I want to make a simple test program. I'm calling it example, and that is going to store the program locally. So we have program, and that is going to contain, let's say, walk with a new line, I think, at the end. That is mandatory. And so new line looks like this, \n, and I need to initialize it, otherwise my editor will complain. And so when we do have a program, then we can provide some input. So let's provide the input maybe before we run the program. So we do some input, and then we have to input every single character as ASCII from our program. So for C in self.program, iterating over all of the characters in the program, we're going to send an input signal with the ORD. Actually, I don't know what ORD stands for, but ORD means the ASCII code of that character. And now if we run it, what happens? We say that non-type is not iterable because... what exactly? I should run example before starting the droid. Wow, cool. So now we actually get some output. It didn't make it across, okay. Well, what I'd like to do now is to see if we can... I wanted to kind of show it frame by frame and pause a little bit so we can see it moving around, but I think I'm not gonna do that, it's not that important. Okay. Funny thing is, you could probably solve this with some kind of random algorithm or some kind of genetic algorithm, because it's very easy to define a fitness function. It just means how far you went. And in the case of this program, you cannot really tell how far it went in terms of how far it went on the grid, or on the line rather. But you could probably tell how many iterations your computer has run. That would tell you something about how far it went. But we are not going to be able to do that. So instead we're gonna use logic and make, kind of come up with our own implementation right away. So in Python you can do multi-line programming by using 3 double quotes. That is very much easier than needing to write /n every time. So here we can say walk, for example. Right. And walk is the final instruction, I suppose. Yeah, when you have finished entering your program, provide the command walk. And I do want to make sure that I'm not starting with a new line. I'm not sure what would happen actually. Yeah, so starting with a new line doesn't work. And also we have to remove all of those white spaces. So I'm going to replace, I'm going to left strip all new lines. And I'm going to replace, let's see, spaces with nothing. Let's see if that works. Yeah, okay, now we have something that we can use. Okay, so let's say that if we see a hole right in front of us, we're going to jump, and just to see if we are able to program the computer. So seeing a hole in front of us means that there is no ground, because the sensor tells us whether there is ground. So let's say that there is no ground right in front of us, and let's store that in the temporary value, and then we're going to, well, we can actually store it right away into the jump register, like this. Now it should already start to jump, and we get an invalid operation expecting something like and, or, and not. Well, that is what I'm writing, but probably it's not accepted for some reason. So let's print our program and see what I put inside, and maybe what is the matter. It looks correct, but I'm removing all of the spaces, also the spaces in between. So of course that is going to give us a very bad lines. So instead I want to strip all of the spaces on the left. I could do that using regex. I don't know by heart how to do regexes in Python. Maybe I can do like, let's see, load program. Let me do it like this and pass a parameter like the program. So I'm going to move this to the outside. I'm going to move it here so that I can write a generic function that would parse input like this. Although actually, if I would write it like this, it's already fine, because I'm no longer having spaces on the left. So that means I can just strip the first new line, and that's it. Okay. So now it actually did jump. We don't get the full output, we don't get everything from the start, we just get the parts where it goes wrong. And so far no one has solved the puzzle yet. And That means that we still are in the running. But also I see that no one is online. Does it mean that it is just a very quiet day today? I think that is what it means. Today is Saturday. It is weekend, of course. So that can be a reason why people like to sleep in. And it's nearing Christmas, people visiting their families. So maybe we are going to be one of the only few online right now solving day 21. So what went wrong here exactly? We are jumping and we see two holes and we're just jumping right into it because we are jumping when we are at the last position. So I think what we need to do is, since we can jump only 3 holes at most, that means that wait a second, we have only 1 jump register, right? And that means that we cannot really say okay, when do we actually need to jump? We want to always land at a hash, and we need to jump if there is an empty space right before us, right? That is like very mandatory. If we are not jumping, then we are dying. So I would put that in the end, in the very end of the script. But other cases we can be a little bit more proactive, and since we're jumping 3 steps, I want to kind of calculate that a bit precisely. So let's say that we have our world that looks like this. You know, having played Mario every now and then in my life does help for coming up with a good strategy. So here we have, let's see, it was 2 blocks and then another one. So it looks like this. And what we want to do in this case is either we jump from here to here, walk, and then jump again, skipping 3, actually 1, 2, 3, going till there, or we can do it 1 later. That is also fine. Actually, yeah, there's really no difference, but we cannot look really far ahead. So let's say that we are here and we actually know that we can jump. So we have 1, 2, 3, 4 positions, so we can see that we could jump there, and we can also see that there is a hole here. So maybe we can just try that first, and then we would just walk forward and see here that there's a hole right in front of us, so we need to jump also. So if at C there's a hole and at D there isn't, then we're going to jump. So there is no ground in C, we're storing it in T, and also, and there is a ground at D, and also our previous value was true, and so if that is true, there was no ground, and there was no ground, and there is ground at D, then we have stored it in T, and then we can just say, well, how do we store it in the jump register then? Maybe we'll just store it right away in the jump register, like this. Okay, let's do it like that. And run it. And it fell. It fell into a hole. Actually, it fell... Oh, it didn't really jump in the end. So should it jump? This is actually the case that we were looking at, and it looks like it goes till the very edge and then jumps. So maybe this algorithm here doesn't work. So not C, store it into J. That means that there's no ground in 3 steps ahead of us, and we're going to jump. And then if there is ground at D, that is where we're going to land, as far as I understood it. Can we verify that? So we're jumping right here, and it says we're falling into the hole. That means that we're actually moving 4 steps. But that should be fine, right? Because we are checking that D has a ground, and then we should jump. So actually, I'm thinking right now if, yeah, maybe, yeah. So in the end, we still check if there's no ground at A, and then we're jumping. And if there is ground at A, then we're not gonna jump. So we're overwriting our jump variable. So we need to kind of do it separately. We need to do some kind of OR. So not A, we can store it in T, and then either T is true or J is true, and that is going to be stored in J. So now we have all of the cases, and it's walking, and then it finished saying that there's something not in range, and that is our output, I suppose. So if the character is bigger than 127, or let's say smaller, then we're going to print it. This is an operation not existent in Python, and otherwise we'll just print the character, and I think it's like steps or something. So that is the number of steps. Let's see if that is right. And it is right. All right. So that was 1 gold star, and let's go to part 2. And I think we don't have sound on our alerts right now. Not sure why that is the case. Let me check that for a second, because I do like those alerts and they should give us some sound. This will just take a very short amount of time. So I do have it set up correctly, I think. Maybe it's just a bit of bad luck. Let's reset it like this. Okay, so we have no sounds today, or maybe you actually hear it, but I don't. That is fine. Okay, so the next part is part 2. There are many areas in the Springdroid can't reach. You flip through the manual and discovered a way to increase its sensor range. Instead of ending your spring code with walk, use run. Doing this will enable extended sensor mode, capable of sensing ground up to 9 tiles away. This data is available in 5 new read-only registers. All other functions remain the same. Successfully survey the rest of the hull by ending your program with run. What amount of hull damage does the Springdroid now report? Okay. You flip. Okay, so now I'm thinking, should we just kind of keep going and that's it? Or should we make sure that we're going to visit as many tiles as possible? Like, if we jump, do we still visit it? I guess so. I see Hans has already solved this part of the puzzle, so maybe it is not that hard. Let's see. So what can we do? That means we're going to have different cases that we haven't thought of before. So let's actually just run it. I'm going to commit. This is going to be one of the quickest puzzles actually in Adventive Code, surprisingly. Even though it sounds kind of advanced when you think of it. So day 21, part 1 completed. And for part 2 we can basically load another program. And that is going to do exactly the same thing for now. And then we're going to adapt it and see where it doesn't work. So we're going to run like this, and we'll run it. And now it did detect a hole as we were supposed to. Oh, hold on. Okay, so here it sees an opportunity to jump, but that doesn't work because, yeah, right after it should jump again. So when it lands, it would land on the right side instead of on the left side. So I think the way I wanted to do it was a little bit different. It was supposed to actually land just right after it. Hold on, where is it going to land? Okay, so it's landing right after the hole, that is correct. Then it's walking forward and jumping again, and that is going to land it into a hole. So in this case it needs to jump right away. So either we jump right away if there is a hole in front of us, that is still fine, but also if there is a hole just one after us and we couldn't kind of jump one step later, then we have to jump now. So we don't need the temporary register anymore. So let's look at this case. We have ground before us. Well, that is actually not important. We do have a hole 5 steps away from us. So there is no ground in E. That means that if we would jump one later, we would fall into it. So there's no ground in E, and there is a hole in there's a hole in B. How can we actually store both of those values? So, and there's a hole in what was I saying? I was saying that there is a hole in E and there is a hole in B. So how can we do that? So maybe we can say not B and store it in somewhere. But if we store it in a jump register, all of our previous logic is going to be removed. Oh, thank you, Eric, for pointing that out. My camera seems to die these days, and that is not very nice. So, well, it's a great face that I chose to make when my camera died. So, happy joy for that. Logitech, let's reset it in some way if we can. Maybe this would help. Yeah, okay. There we go. Thank you, Eric, for pointing that out. That is something I wouldn't notice myself, because I finally made the habit of not looking at my own video recording while streaming. Thank you. So, we making a jump. Okay, so now I'm kind of thinking how we can track both of those states. I'm going to use the whiteboard again and see if we can come up with some nice strategy. So actually the strategy here is not so much about when to jump. That is pretty clear. The strategy is how to use those 2 registers that you have and use them wisely. So we have the jump register and the temporary value, and we have our cases when, what was it? When there's no ground at C, so that's like 1, 2, 3. So here is no ground, and there is ground right here. Then we're going to jump, and that is position 4. Right. I'm thinking maybe we can actually so maybe we can make J true. Wait a second. I'm having a little bit trouble of how to actually debug this and how to think about it mentally. So let's just do it one more time. So after this point, we have decided that we're going to jump in a last resort action. And here I want to keep track of, I want to look at which case exactly. So we are jumping already here. That is not right. We're jumping here because we see a hole at C and we see a ground right after it, and so we're jumping. Actually, that is not so much of a problem. But then here we should not wait until the very end. We should jump proactively. So we cannot touch the J, but we can. So not E means that there is a hole in E and we need to jump before. Let's see, I think the more important part is that there's no ground 2 steps ahead of us. Yeah, and that we can store like here. And also, I know something maybe what we can do. We can check that there is, yeah, I know what we can do. Okay, so what we can do is we have only two writable registers, right? That's A and T and J. Yeah. So let's say that we are checking that B. Wait, hold on. How can I make T false? Is that possible? Yeah, I can. So not B, and then I want to do... No. Sorry for that, I'm just kind of going around in circles, but the idea that I'm having is, what if we check that there is ground in B and E, and then doing a negation of that? But that is actually not equivalent. So what we do want to check is whether not B and not E, that should be the same as, so not B and not E, that means either B or E, right? B or E. Or was it not B or E? So we need to have no B and no E. And no E. So if either B or E is true, then it means that this part is true, and then we are going to negate it. Yeah, okay, so those two are equivalent, and it seems like my whiteboard didn't activate. So I'll show you that once again. So the case that I want to cover is where either there is no B, I'm drawing it like this maybe, if that's more familiar. So B, not B and not E, that is equivalent to not B or E. And maybe that will be a little bit easier to implement with this little droid script. So if we have no ground in either B or E, so how can we do that? So or B, and then we need a temporary register, but I want to find a way to reset the temporary register, and I don't have a way, but I could of course store like A into T or something, like and T and A and T, and then store not T. No, that also wouldn't work. I can do maybe I can store not A in T and then do and A stored in T. Yeah, like this. So if A is true, then T will be false. And then I'm checking if A is true and T is true, which is never going to be the case. Then basically I'm storing that in T, so I've basically forced T to become 0. That is handy. So now T is definitely 0, and we can use it for good. We can decide whether B or E. So either it's B and either it is E, and we store it in T. So now we can actually like store B into T and otherwise store E into T, and T will be true if either B or E is correct, or is true. And then we're going to negate it by saying not T and store it in T. So now we have the case where T consists of true if there is a hole 2 ahead of us and 4 ahead of us, or 5 ahead, 1, 2, 3, 4, 5. And in that case we're going to have to jump. So I'm going to store that somewhere, and I'm going to do, we're still going to jump if we were jumping already. So now this is the way we can do that. And I want to strip new lines from this, because I like having these sections, and maybe I even like hashes. Reset T. So we're going to filter our program. We're going to split it by new line, and then iterate over it. Line for line in program. And if the line starts with a hash, then we're going to skip it. So if it doesn't start with a hash, and if the line is not an empty string, like that. And then we're going to have to join it in the end again using new lines. And a new line is like this. So now we can actually add comments, and that is very handy. Resetting T. Okay, let's see if it works. Run. Okay, so it is asking for input. That means that we didn't provide it any input. That means also that what is going wrong? I'm printing the program also. You see that it doesn't print anything. So apparently what? The line isn't an empty string. Have you forgot the new line? Oh, the last new line. Yeah. Thank you, Alex. Yeah, I did. It looks like that. Alright. It's running, and it's running quite far, I guess. Yeah, so Alex, you're also done already, an Arcadian Archer too. Okay, cool. I feel like this is probably not going to take that long, but you know, who knows. So I guess there are going to be those cases where you're not supposed to jump at all because something would go wrong. And that is the case here. So we're jumping on the first available platform and then jumping right away, but we shouldn't do that. Maybe we can do a check in the very end to see that maybe we should cancel our jump, something like that. That's what I'm going to do here. Cancel if we would do a double jump. If we would need to do a double jump. So why can we not jump here? What is the reason for that? Because we would end up on the first available platform, and from there we cannot actually jump right away. So basically, if we have the case where A, B, C, D, E, F, G, H, how does that look? So we have basically two empty spots. Oh, wait, two walls, one spot, one hole, one wall, one hole, and two holes. Yeah. And you say, Alex, you didn't like today's puzzle particularly. You thought it was missing the information that all jumps have the same distance. Oh yeah. Well, I found it out. I just ran it and I saw it jumps 4, and that was it. Oh, so yeah. I guess if you misinterpret that, or you thinking about how long to jump or something, then you're spending a lot of time in the wrong direction. Ah yeah. Okay, so this is our case actually where we should not jump. And that case is going to be when there is not C and we have not E and not G, or not H actually. That is like this. So if we're jumping from D, we would skip 3 and end up in H. So that H is the crucial part to check. So let me reset T again, just to make it easier to think about what we're doing. So if not all of those, right? If and not C and not E and not H, that means not either C, E and H. So that we know already how to solve. So basically we do OR with T every time. So C, E and H. And then store not T and T. So now we know that if T is true, then we need to cancel. Or maybe if not T, then we need to cancel. Yes. So either, so that means T is true and J is true, then we can run it. Let's see, and we're out of memory. At most 15 instructions can be stored. Oh no. I forgot about that requirement completely. So maybe we can actually not reset T. How many instructions do we have? So let's check that. I'm actually going to store the program as a list of lines, and then before inputting it, I am going to just, let's see how we do it. We're loading each line, and then for each character we're going to input it like this. And I'm going to add a new line in the end as well. So that is not print, that is just passing input to the computer. That is a new line, and that would work. And then it means that I can show some information like checking how many lines we have, printing the program, and printing the number of lines. Like this. We have 18 lines, okay. But you do like how you're writing in a code for an encode interpreter though. Yeah. It's kind of crazy, right? That we're writing a script that can be parsed by a computer that we built ourselves. But I would like to learn how to make a Springdroid like this, how you write a program. Eric, did you write your own compiler for this? And what kind of script are you using to come up and design these programs? Did you write debuggers for it and such? Because it's not easy, I suppose, to write it in assembly directly. Did make an int code assembler. Ah, I see. Well, that's something I would like to do too. Can we learn about how you can do that, Eric? Can we learn that, or are we going to learn that? If you don't want to spoil it, that's fine, of course, if we're going to do that in Advent of Code. In that case, you might say, yes, you can learn it, I will share it after Advent of Code. And then if it turns out to be one of the puzzles, then it will be, of course, clear what the situation was. So we can store only 15 instructions. And how about resetting T? Maybe, yeah, T could be true. And we have space for at most, how many? I think 13, right? Wait, at most 15 can be stored and I'm having 18, so I need to remove 3 instructions. So maybe what I can do instead is this is tricky. I need to remove 3 of them. So I can do or with the J, with the jump register, but then I'm going to have to reset J. Maybe I can remove one of these. So I want to store... Hold on. Maybe I'm checking it in a too kind of complicated way. So here, maybe we can say that we want to jump not here, because H, it has a hole, something like that, because E and H have a hole. So we need to kind of specify that condition all at once. So I'm going to load a different program now. So that's Droid load program. Load program with some data. And we have the specific cases that we want to address, and this is one of them. And the basic case that we had was the case where we are here and we have a bunch of holes and we can just jump to it like this: A, B, C, D, E. Was it actually like this? Let's see. So originally, if there's no ground at C and there is a ground at D, then we're going to jump. So basically like this, right? And then we would, right, actually like this. So our robot is a little bit to the left of the 4 tiles that it can read. So if we see a hole at C and we have a ground at D, then we're jumping. But let's decide to do that only if there is not also going to be a hole. Like, let's say it looks like this. Or, well, there are some parts that we don't know. But for sure, if we are here and we're going to have to jump, because here is a hole, then we would end up here, right? So there must be there must be ground there. If there's no ground, then we should really not jump. But that's only the case when there's a hole here. If there's no hole here, then it doesn't matter that much. So, so there's a hole. Oh, I think someone's alarm is going off. 1 second. Alright, I'm back. That was my girlfriend's alarm. Still being set to working mode, I think. Luckily, she can sleep in today because it's Saturday. And I'm gonna try not to wake her up. So, what I was saying is I wanna jump if C is empty and D is ground, but not if E is a hole and somewhere else we have a hole as well. But that would be E, F, G, H. So H must not be a hole, and the other things in between, we don't really care. This doesn't matter. This doesn't matter. At least for now it doesn't. So let's see what we are looking at. B doesn't matter either. A doesn't matter either. So we're looking only at C, D, and E, and H. Okay. So our new program is going to do this. It's going to check. Let's keep two variables like... What can we do to check this? So either we have the simple case where we can just jump, and that would be the case where we have like A, B, C, D, and our robot is here. That is like this, that's the simple case, and the other case is the complicated case. Well, I'm not sure if I can kind of redefine my strategy, and I must say it is so hard to read this assembly code. Like, I'm looking at it and it just doesn't mean anything to me, even though I just wrote it. Well, let's look at it again. So we start by saying if there's no ground at C, then jump, for now at least. And if there's ground at D, then you can jump. Maybe we don't need this. Maybe we can just say jump anytime that there's ground at D. That could make it faster and shorter at least. But now the question is, how do we store, how do we write D into J? And we can use OR, of course. So J is 0 by default, I think. The jump register is true, no. So what are the default values for those? They start with false by default. So basically we can say either D or J, and then we just jump. Unless, so there must be, there must be ground at J, and then we're gonna jump. That's it. Okay. Maybe we can just run it. And we're not gonna load our other program, because now I think we've actually removed a few lines, but it did die. It did die actually very quickly. So either D or J, and then we're going to jump. And D means the place where we're going to land. That's how I understood it, at least. And here we have a cancel logic that is going to cancel it. And maybe that is what is messing it up. So when we have some land at C or E or H, and none of those cases is the case, then we're not gonna jump, and so we're storing the negative of that in t, and then we must have t true to be able to jump. But looks like we broke our code, so let's run it first without that second clause, and now you see that it actually goes a little bit further, and the second one is running. Now I did turn it off correctly. So it means that our kind of cancel logic is not correct. So we are resetting t, that is fine. Checking a is not true and storing it in t, and then checking a and not a. Then we always get 0. What else? Then why doesn't it jump in this case? So we have A, B, C, and D, and we're saying that C is a ground. Let me write that down actually. This is our case. A, B, C, D, E, F, G, H. Okay, so C is a ground, that's what we're checking for, and that is true, so T will be true. E is ground and it's true, and H is a ground and it's true. So T is definitely true by now, and then we're saying not T, so T will become false, and then we're actually saying that we shouldn't jump. So that is not correct. So we have ground in C, E and H. Why should we not jump if we have ground there? It is rather that if there is holes in all of those, then we should not jump. So maybe we shouldn't reverse it, we should just do it like this. So now, yeah, maybe. Okay, we want to make sure that we have all ground everywhere. So to have ground everywhere, we basically need to do AND. So C is true, and E is true, and H is true, and then if that is not the case, then we are going to cancel our jump. So not T stored into T, and then we cancel it. Or maybe I don't need it. Yeah, I think once we know for sure that we have ground everywhere, then we can say that that must be the case as if we want to jump. If that's not the case, then we're not gonna jump. Right? Not sure. That didn't work exactly. Maybe it's because we have a final case where we want to avoid jumping when there are 3 open spaces. Then, oh, we didn't jump at all here in this case. Maybe, how many lines do we have left? We have 14 lines, so we can do one more line. So maybe we can actually jump either if... Maybe this cancellation logic is a little bit too strict, because if we have this particular case, C, E, and H, C, E, and H. Yeah, so actually we're talking about the case where we were gonna jump, right? So if we were gonna jump, then we need to check this. But if we were not gonna jump at all, well, okay, then we wouldn't have affected anything. Maybe. So this is actually not really the case that I'm trying to avoid. The case I'm trying to avoid here is where H doesn't have a ground. So that is the case where we're jumping to go to... What is it actually? Is it like this? Let's see what happens. So here's the case where we are dying because we are canceling too early. So I'm not sure. This is the case where we are dying, but it's not the case that I was handling before. So if we have maybe, okay. Sorry everyone who's watching, I'm still kind of biting my teeth into this problem, and it's still early of course, and my brain is not completely functional, but oh well, we can try to get somewhere. So here we need to jump, and I thought that I already solved that, but maybe because I removed some of the code here in the front where I'm saying that we are jumping when D is empty. Oh, when D has ground, then we're always gonna jump. And here there's the second case. Okay. How about jumping also when 1, 2, 3, 4? Yeah, I'm not sure why we didn't jump there yet. Why didn't we jump? We actually did jump. We jumped and we landed straight in front of the hole. And because of that, we now end up at a situation where we cannot actually jump on time. Yeah, so basically that's the rule. Maybe the rule is always jump unless your jump is going to end you up in a hole right after. Okay, that sounds like a simple logic. So I'm going to make a new program, and it says that always jump as long as the place we're going to land is going to be filled with a wall. But we also need to be able to see if there's a hole afterwards. If there's a hole afterwards, and also 4 steps ahead, then we should cancel. Okay. So let's say that we're storing whether there is a hole in I. We need to check it before the jump actually. Before we reach that cliff, we need to have already decided that there might be some problem here. So we jumped from here, like from 1 to 2, that's how we jumped. So at the position of 1, we need to know that we cannot jump. And that case was like this, right? That was the case, because when we are at 2 and we need to jump, it's 3 steps and we would end up in the hole. So that means E and H are open. So we're jumping as long as D is a landing zone and H is also a landing zone, I guess. Although, yeah, I guess so. So D and H must be a landing zone. Okay, so let's store D. I'm just gonna store it in T. So D and H are going to be stored in T, and then either T and that is stored into J. Maybe that's it. Maybe that's everything. It's still asking us for input instructions because I didn't say a run. Oh, it did fall actually. So in this case, you know what? I'm going to hack into my output and see that if I find a new line character just after a hash, then I'm going to print a row of A, B, C, D, E. That would help. So that means that, like let's say if C equals 10, maybe I can keep lines or something. Output lines is nothing, and I'm starting with a line that is a string, and I'm going to append it. The line plus equals the character of that character code, and otherwise we're printing the number of steps and breaking out of the loop. And at the end of the line, maybe, so we're appending, and if the line, no, if the character is a new line, then we're going to print the entire line. And also, if our line contains... That doesn't exist, but we can do it like this. If a hash is in the line, then we're also going to print the alphabet, or at least a part of it, like this. And that is it. So let's see what that looks like. We're printing now mostly the alphabet and nothing else. And why is that? Output lines is no longer needed. Okay, I see. So if our line ending is if our character is a new line, then we're going to reset our line. Something like that. I think I have to go over that logic again. So our line is empty. If we have a character in the ASCII range or appending to the line, and if the character is 10, which is a new line, then we're going to reset our line and then print it. Maybe the other way around would work a little bit better. And if a hash is in the line and we are at the end of the line, then I want to print the numbers, yeah, the letters, like this. That is helpful. So why should we not jump here? We have a space at D and not at H actually. And I'm printing it a little bit wrong. Oh, here, why should we not have jumped here? Because D contains ground and H contains ground. That is fine, right? So we can jump to D and then we jump again. So we jump and then we... Oh, we don't jump. Because actually H... Okay, do we have more registers actually? Can we go all the way up to V? For the second part, what do we get? We can go all the way up till I. Oh, that means up till here. And here we know we should not jump, because if we jump we end up at D, and then we end up at H, and then we end up somewhere else, but we cannot see it. But we can see that I is empty. Maybe it's a little bit too proactive, but it's not clear at this point that jumping would be unsafe. But of course, if we have only walls for the first 4 steps, then we don't have to jump really. So let's avoid jumping when there are 4 walls. And that means, yeah. So if there are 4 walls, we can just not jump, right? And we can just walk, and then we have a little bit more chance to see if we can actually jump later. So how do we know we have 4 walls? We can reset our T value using this trick. Comparing A with not A. And then do we have 4 walls? Blue Pichu gives a concise example why this problem is in general unsolvable. Wow. But that means that the input must be in such a way that it is solvable. So if we have 4 walls, then not jump. Right? So basically, we're first starting by loading A into T, and then we're checking B, then we're checking C, and then we're checking D. Then we're checking not T and storing it in T, and then we must have not 4 walls and we can jump. So, and we have not 4 walls and we can jump. Like this. And it still fell. It still fell. Okay. Test cases. That is a very good idea, by the way. But to make a test case, I would have to implement an Intcode computer, or I would have to I would have to implement this Droid script, or I would have to simulate it. So we are not jumping, so that looks like it's correct. The Intcode computer does the test cases, you guess. Yeah, that's true. But if I want to set up a specific case, like this specific case, I don't know how to do that. Well, I could kind of store the state of the Intcode computer, of course. So here we are not jumping, but why? So this is true when all the walls are filled in, and if not all the walls are filled in, then we have true. So we have some holes, and then we can jump. So we must have an empty spot, like an empty hole somewhere. But I think D should not be included in that. Because if the... hold on a second. What is this about? So if D is empty, then also we can't jump. But why aren't we jumping here? And that is the problem with not having control over the droid. That I'm not sure if I'm not jumping because of what happens above or what happens here. I can try to reason about it, of course. So let's see, we have... oh, wait a second. A, B, C, D and so on are not offset correctly. They have to shift together with the add sign. So I'm going to have to keep the X position of the robot, which is none by default. And let's see if the character is actually an add sign. That means we know the robot's position, and that is basically the length of the line so far. And then we're going to append before a number of times a space like this. We repeat it with the X position plus this other these other letters. So now it looks like our letters are actually moving along, and I got it right at once. That's very nice, but it was a bit of a guess. So here we have the case where the robot should really start to jump, but it's not jumping because D is right, but H is not right. And that was my kind of condition here, that I should jump only, my second program, only if D and H have grounds. But that is not necessary, of course. So maybe I should jump not when D and H are grounds, but when there is either a ground at H so that I can jump twice, or I have some ground before, maybe like that. So either H has ground or E has ground, maybe like that. So let's see, so D has ground, so we can jump to it, and H has ground. And also maybe we can do it with J. We just store it in J right away. And so yeah, so now we've stored it into J, and now we want to make sure, so either D and H must be walls, then we can jump, and or we jump if there's a ground at E, like that. But I want to jump only if D and E are true. Oh man, a lot of different cases. I think this is not working. I'm running it, but I know that it's not working. So even with the first hole, it actually breaks. It's jumping right into it. First thing it does. Okay. So we want to jump to D. You know what? Let's always jump to D. Let's see what happens. So we're always jumping unless we have 4 walls in front of us. So that means that it went a little bit further until it saw that D has a spot, and there's some wall there that we have to, some hole that we have to pass. But if we can pass it a little bit later, then maybe we should do it later. But here's exactly the case that I wanted to avoid, right? So we are jumping onto a platform, that is correct, but afterwards we have to jump right away, and we can't. So that means that here in this case, it is the case where E and H are also holes. Yeah, that's what happened before. E and H are holes, then don't jump, right? So let's store E into T, and we cannot do that. We cannot also check not something else. So we are going to have to reset our function again. I think I'm doing the same as before, kind of. So not E into T or H into T, and then not T. Hold on. So if they are holes, then don't jump. So they must both be walls. So basically, actually, it's easier. So it is the case that E and H must be grounds, and if they are, then we can jump. Oh, like this, right? Does it work? No, still not. So we don't jump here because E and H are not both. Oh yeah, and wait, this is only applicable when there's a hole right after D. No. So, hold on. The case that we were dealing with was, which one exactly? This case, right? Oh man. Okay, thanks for hanging out, Arcanian. See you tomorrow, and good luck with tomorrow's puzzle. Bye. So, okay, we did jump here, but we shouldn't have, and we decided to jump at this point. Yeah, this was the point where we decided to jump. Okay, a little bit of fiddling with my cursor. So we cannot jump because E is a hole and H also is a hole. That's why we can't jump. So either E must be a wall or H must be a wall, right? So here we go. So E or H are a wall. And so we're resetting T. And so either H is a wall or E is a wall. Maybe like this, E or H. And then T must be true to be able to jump. So and T and jump. Okay. Now we have 15 lines exactly, and we are running and we get an output. Yeah. And it's right. Okay, cool. Wow. So that is a bit of assembly coding. That's the first time I've done something like that. It is of course very primitive assembly and it has 2 registers, but it does kind of help me to get used to the idea of programming with very little variables. I remember from TI-83 programming, the calculator programming, that we had only 26 variables and it was very tricky to be able to store everything you needed. But in this case we have only 2. That is really a whole different level. Especially that also the fact that you can't make complex expressions like either or and you have to reuse the same variable and kind of go over it. That's a very interesting way of programming, and yeah, something I see how you can get used to it, but it is a skill on its own, I think. So assembly programming is really a whole different ballgame. Well, let's commit it, and let's see, Zarankiewicz, do you have any code to share today? 21 part 2. And thank you, by the way, man, for your solution to puzzle 20. I was stuck on it, and by looking at your code, I found out where my breadth first search is breaking. So I found out that I actually didn't understand breadth first search correctly, and so I now know how it works. And I am also going to be able to apply it to puzzle 18, the one with the doors and keys. So I will be able to finish that today, I think. Yeah, thanks very much for that. I'm learning so much during this advent of code. So let's see, this is your program. Okay, do we have the same thing? Do we have the same algorithm? So you have part 2, and it looks like... yeah. So I have all of my comments in between. And you have... so either not HJ. So let's actually look at what that looks like. So I'm going to write a bit of comments here. And we have A, B, C, D, E, F, G, H. A, B, C, D, E, F, G, H. It looks like something is wrong about it, but it's actually correct. And so here is our droid, and then we have some walls. So I'm checking all of the different cases. So for case 1, or line 1, that is not H, and then jump. Basically like this. And then you're saying not jump, then jump. Interesting. So if there's something at H, then you're going to not jump. Is that the case? Then or there is a wall in D and stored in T, and also E. So D or E is a wall, and then either you're jumping and that you have a space at D and E, and you're storing that into jump. Basically, you're deciding not to jump when there's an H, and when there is... am I reading it correctly? When there's no wall in J, then you're jumping, but then you're saying, no, we're not jumping. You forgot what it does. I can imagine that. Yeah, me too. I wrote some comments, but even that, like, it's write and forget or something like that. So here you're saying don't jump, like I'm just writing it down. So line 1 and 2, I'm actually copying it here and just putting it into my robot. So droid.load program. So up till here we say don't jump if H is a hole. Okay. And then we're saying D or E are holes, is a hole, and then we're jumping also. Do jump if D or E is a hole, but actually, if you do that, if you jump if D or E is a hole, then you're going to jump into a hole because D is the place where you land. But maybe you're just using J as a temporary variable. So if D is ground, then we're jumping. So if D is ground and D or E is a hole, then jump. That is the same as saying if D is ground and E might be a hole, then jump. Right? Because... oh, wait, I'm reading it wrong. It's D and E is a hole. Okay. So if D and E is a hole, that makes a little bit more sense. Then we're jumping. So if D is ground, then jump. But that... wait a second. How can D be true? D is not a hole. So when D and E is not a hole, How am I reading this? I'm reading it incorrectly. So D means that there's ground at D, right? And E means there's ground at T. Oh, is not a hole, is ground. Damn. Okay, so when D and E are ground, you jump if D and E are ground. And then here we have, if D is ground, then jump. Right? Yeah, because this first part, not a hole. If H is not a ground, then we're jumping, and then if we're not jumping, if we're jumping, then we're not jumping. So here we have, if a hole at H, then jump, and then if not jumping, then jump. So it means if a wall at H, then jump, right? I think that is what it means. If a hole, then you're jumping. Now, if not jumping, then jumping. So it's the other way around. So if a wall at H, then jump. Okay. So then D and E are ground. You jump if D and E are ground, or H is a... Yeah, or H, or we were jumping. So that means when H was a wall. Yeah. So basically that is D and E or H. Yeah. And then if D is ground, then jump. Okay. Jump only if you were jumping already. So yeah, here I think you have a double D there. So D and E or H. That is what we are doing now. Yeah. Or we are jumping and storing that into T. So basically we're checking if we are jumping. Are we jumping? Store it into T. And then we're checking A, B, C, and not T. Ah. Okay. So this part is doing A and B and C. And then you're doing not, storing it into T. And then you're doing and jumping. And jumping. C and jumping. So what does that mean? Alex, do you remember actually your kind of conceptual strategy? Did you have it drawn out or something? I suppose you must have, you must know kind of what you were doing conceptually before you made this, obviously. Basically what I'm trying to get at is, what is the strategy? Like, my strategy was basically keep walking, like don't jump over straight lines that you don't have to jump. And otherwise we're just always gonna jump basically, unless you're gonna end up in a position where you have to jump twice and the second jump is going to fail. That's it. You do remember that the end was because it jumped over ABC even though ABC were walls. Yeah, okay. So that's exactly the same thing as I had. So you're checking for E and H as well. I am checking for E and H. And you are doing that also. Where here is H and here is E. Yeah. Your program failed on the input where there are walls at A, B, C, D, G, H. Ah. Oh wow, okay, yeah. Yeah. So here you have a check that checks if A, B, C are all walls, then only if that's not the case then you can jump, otherwise you can't. Yeah, well, I wouldn't say that mine is readable as either. It's just very hard to kind of figure this out. Hey, mistakes were made. Good evening or good morning. Thanks for sharing your code. You have part 2 pasted on pastebin. Let's have a look. Thanks Alex for sharing. I'm sorry everyone for being so bad at reading assembly-like code. This is the first time that I'm doing that. But maybe we will get better as we go. But it's nice to know that we did have the same approach, and you can apparently check for those 2 cases separately. But the conclusion for now seems to be that you always jump, right? Unless you're not supposed to jump. So always jump, except for specific cases where you know for sure it doesn't work. Yeah. So if there's a hole in front of me, jump. There's no other choice. I like the comments you added there. So if there's no A, then store it in T, and then either T or J. Ah. But you can actually store it right away in J though. There wouldn't be any difference. Except if you wanted to keep T for some other purpose later. Yeah. Okay, so if there's a hole at 2 and then you land at 4, yeah, then jump. So if there is no B and there is D, then you're going to jump. Okay. So you're actually handling all of the cases separately. I like that. That is actually kind of clean. And we're only allowed to jump if we have a space to move when we land. Well, that's interesting because the way you phrased it there is different from how I phrased it. I said we are only allowed to jump if we land and if we had to jump again, that at that particular spot would be land. But maybe that's what you're doing. Ah, yeah. Oh, okay, that's what you're doing. Meaning there's a landing space at 5 or at 8. Yeah, that makes sense. So that is like E or H, right? Do I have that in my code? Yeah, I have it as well, E or H. So I have it defined in the other way. So I say if E and H are holes, then don't jump. And you're saying if either E or H are walls, then you can safely jump. But it is a requirement for jumping in general. So you're saying, oh, you're saying J. I'm not using J at all. Oh, wait, J is your register for jumping. Right. Okay, so either you're jumping, then you store it at T, and E is a wall, then you can still continue to jump, and or H is a wall, then you can continue to jump, and then you say, yeah, it must be true to keep jumping. Yeah, that or JT thing was to get T into a known state. And how do you know for sure that you get a known state? And this state is going to be true then, I suppose. But how do you know for sure that this is always true? So here you're storing whether to jump in, whether T is true into J. Okay, so you're always... I'm not so sure. Because right before you do or TJ. Yeah, okay. So or TJ and then or JT. But still, I think, yeah, so T equals J at that point. That is clear that they are the same. But if they're the same, it doesn't mean that you would get true. Yeah, it means it's true if you've already decided to jump. Yeah, that of course is the case. So that means that your conjunction is not going to trigger if you are not gonna jump, and that is fine, because then you're still not gonna jump in the end. So you're adding an additional constraint on your jumping logic, but you are not jumping anyway. So I guess You just need to know that it's true when you're jumping, right? So let's say that T was false, and then you're saying, okay, but E must be a wall if you're gonna jump. But if you're not gonna jump, it's also fine. Yeah. Okay, then we got that right. Yeah, that's a nice way to solve it. I like it. I like that you start with A, then B, and then C, and then the case where you have this tricky part where you're jumping twice and you would fall. And you managed to do it within the number of lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 actually, with 2 lines left to spare. I guess the challenge for today, for those who are very excited, is to try to make it as short as possible. I think you can probably make this smaller somehow. Your thinking was enumerate the cases to jump and then prune if a bad decision was made. Yeah, that seems to be right. Alright, thank you very much. Mistakes were made for that code share and clear explanation. I am going to just play with it a little bit and see if I can make it smaller, just for fun. I'm curious what the smallest program is that can actually pass this puzzle. So I said at the beginning, I think that I do have to get rid of those special characters like this, and no commas in the end, and then go all the way to the left and replace this with a hash. So I did say that you could technically store not A in J directly, and you didn't need this line. Yeah. So let's run it. It's 12 lines. It takes a bit of time to run. I don't remember my output. So I guess if it outputs anything, it should be correct. I can return and double check it. Wait, what is this? I double clicked by accident. Okay. So the output is 11 something. Yeah, so that is actually the right answer. So we now have, how many lines? We have 12 lines now. And you're saying you can definitely make it smaller if you don't insist on putting everything in T before J like you were trying to do. Okay, so you're saying kind of that we could store things in J. For example, let's see where we can do that. So if not B and T, yeah, okay, so here you're kind of saying T should be correct, T should be true, or J should be true, and then we're gonna jump. So you're adding another case for jumping. Let me see if we can make that smaller. So the other case for jumping is when there's a hole at B and you can land at T. So maybe we could say, no, I'm not so sure if this part could be made smaller. I would say no for now. Although we could actually store T, right? We could use only T here and not store the jumping yet. Is that possible? So not C and D. Well, here we have 2 lines that are the same. Basically what you're trying to do is to see if 2 or 3 are holes and you can land at D, right? Maybe we can combine that into a single statement. So right now it can still run. And what if either 2 or 3 are holes? 2 or 3 are holes when we basically say either B, either C. So now we have holes there. So we need T and D, and that will make us jump. So maybe now we can actually run it like this and it would still work. No, it didn't work. Why not? We have to negate it first. So not T into T, and then we have one place where there are not two walls, and then we have a wall, and then we're gonna jump. So like that. And it didn't work. So now I actually just broke it. I'm going to revert that so that I won't lose the code that was working before. So this one is going to be replaced with something shorter. So either B is a wall, or C is a wall, and then not having the opposite of that means that there is a hole in there. And if there's a hole in there and D is right, then we're going to jump. So we could do it like this, checking D and storing it in T, and then T or J. So we're gonna add another jump case, but that doesn't work. Why is that? Why is this not equivalent to this? It could depend on T, maybe. Maybe T, no, T should also be 0 by default. So here we're doing, oh, wait a second. I think I might have changed something in the code. Let me double check. Oh yeah, the original code was not B stored into T and D stored into T, yeah. So there's a hole in 2 or 3, and there is a landing at 4. Not combine 2 and 3, so that means if 2 or 3, then jump. 2 or 3 and D, then jump. And let's see. Actually, we are checking for holes, right? Not 2 or not 3. Not 2 or not 3. Is that the same as... is that the same as not 2 or 3? I think that's not the same. Not 2 or 3 means that it's not both false, or it's not both true. That is why it doesn't work. So we don't have walls in both sides, then we can jump. Yep, that seems to be running also. So now it's smaller. And it's not very much smaller, it's still 11 lines. And now I feel like we have basically the case where when there's a hole right in front of us, then we need to jump. This case could be also added into this, maybe. Because basically it's like not 1, not 2, or not 3. So you saw a solution with 8 lines. Okay, let's see if we can get there. So this line I'm going to remove. And let's say that we want A and T and then store and A and B. So basically if there's any hole in A, B or C, then we're jumping. That's kind of the logic that we have right now. I didn't save any line by doing that, but this is the same. And now basically what we could do is using the jump variable instead of the T variable. That could help. So like this, and then we can just store, no, hold on, or T or J. That makes no sense. It's just storing T into J. You saw a solution with 8 lines and it was also easy to read. Well, we are going to have a look at that in a second, because I am also curious. But I'm also curious to see how far we get. So either 1, 2 or 3. 1, not 1 or not 2 or not 3. You know what, I'm actually going to remove those @ signs. They look nice but hard to type. So like this. How can we make this a bit easier? So not 1, 2, and 3. Ah, I know. We can do AND A and B stored into T, and then C or T and... No, that's not how it works. We have to check A and B and C like this. But I think that's still the same number of lines, and it's not working right now also. I think you can do what you were about to do and change all of the T's to J's and remove or TJ. I'm not sure exactly. Let me revert that. Oh yeah, and the first one always should be or. So now it's still working, right? Yeah. Okay, let's see what happens if we do that. So this is the working piece of code, and now let's try to make it shorter. So either A is a wall, B is a wall, and C is a wall. And then we're saying, well, if that's the opposite, so either any of them is a hole, then if D is true and we were jumping, then we're still jumping. Okay, yeah, you're right. That is actually equivalent and shorter. So 10 lines. 2 lines to go. And then we're only allowed to jump if we have a space to move when we land. And so yeah, either we can jump right to the next one. And that's cool that you've already assumed that you're gonna jump because of the next steps. So now we can say that either there's something at 5 or 8. So T is not used so far. That is very handy to know. So T is still 0. So we could use AND basically. No, we couldn't. Let's see. So what you want to do is to check J or no, E or H. That's it. So E or H must be true. So we could do it in a simple way that is like E stored into T or H stored into T and T and J. That's it. Right? That is one line less than before. Okay, that works. Awesome. Nice. Getting somewhere. Now we're still using the T variable. Maybe that is something we don't need. I'm going to remove... Yeah, okay, so basically this part is like if not 1, 2, 3 and 4, this is all going to be removed. Just remove the run and we're done. Oh, they didn't write run. Oh, cool. No, that's nice. Very proud of us to be able to get to that point. But can't we make it shorter then? But you know, the funny thing is you can make it more shorter. You can make it more short, but I'm not sure if it is... Like, if you read this code, you know what it's doing, but do you know that it's gonna work? That's not obvious at all that it is going to work. So we haven't checked E yet. So I'm thinking now, since we are doing these OR cases here, can we reuse that? Can we reuse this logic in some way? No, we can't. So our basic logic is if not 1, 2, and 3, and it's 4, and G and H. No, E and H, so that's 5. And what is H? F, G, H, so 3 more. So 5 and 8. And 5 or 8. Yeah. Yeah, can we simplify this even further? So 5 or 8 must be true. And 4 and 5 or 8. 5 and 8. Or 5 or 8. Yeah, I feel like... Yeah, no, I guess this is the shortest that we can make it now. I am not sure. Any other suggestions? For making this even smaller? We are still using a t variable here. But... yeah, I'm not sure if we could actually avoid doing that. Maybe. Yeah, I am comparing here E or H, so we cannot actually use J here, because then we're comparing with the jump, whether we jump or not. But let's say... let's say we were jumping already. No, if we do this, then we're just gonna jump whenever H is true, and that's not what we want. We wanna stop jumping. That's what we're doing here. Avoid jumping. Well, doesn't it mean we are avoiding jumping when E is a whole? Or when H is a whole? No. Yeah, you're not sure if it would help, but you could do the 5 or 8 part first, directly into J, and then do the rest ending into J. Okay, let's try that. So... ah, yeah, I see, okay. So this is what you mean. So either E or... okay, so we could store it directly into J. So now we know that we are allowed to jump, and then here we can do and instead of or. That's what you mean, right? But I feel like now it's really not gonna work. No. No. Doesn't seem to work. Yeah. Okay. Because we have decided that we have a case for jumping. Kind of a case for jumping. But it seems like we do need a t variable here. And we can do that actually, and then we just say and tj. Isn't it the same? But now we have 9 lines instead of 8. Yeah, not sure how we added the line by just reversing it. I thought that we had 8 lines. Oh yeah, it was 8 lines. We didn't count the run. Okay, so it is equivalent actually. Yeah. Okay, cool. I guess that is, we've exhausted the creative possibilities of day 21. So I'm going to end day 21, but of course that doesn't mean that the stream is ending, because I'm still working on day 18, for which I have a solution at hand, I think. It is the one with the puzzle where you have to open a lot of doors with keys. And my breadth first search is broken. So thank you all for watching day 21. See you again at day 18, the final part.